Hello and welcome to section 5, Missing at Random Gradient Ascent. In the previous lecture, we actually got stuck here when we wanted to calculate the CPD of this part of the network using a data set with missing values. Even when the missing values were at random, we still couldn't solve this case because the parents had missing values. So how can we solve this? Well, to recap the problem, we had this proposition that under MAR, if the parents didn't have missing values and also Xi didn't have missing values, or still the parents didn't have missing values but Xi didn't have a child, then we could just use the MLE method that we previously explained. No special difficulties here. But what if the parents have missing values, as in the previous slide? Well, in this case, we can use one of the two approaches, gradient ascent or expectation maximization. And in this lecture, I'm going to talk about gradient ascent. So what is gradient ascent? Well, the goal is to estimate theta that maximizes the likelihood. So this is basically an approximation for the MLE. In the MLE, we could estimate it. We could get the exact value. Here, we're going to get an approximation. How does it work? Well, we can summarize it in the following steps. We start with some random initial condition. Say here, this is our likelihood function. This is actually our log likelihood function, L, small letter L, that we will use. And you see that it has some local minimums, local maximums. The global maximum in this case is this one, which happens for this value of theta. We start from some random initial point, for example, here. We compute the gradient of the log likelihood. Again, this is our new notation, small letter L, at the current solution theta hat. So my theta hat now is theta 0. I calculate the gradient. In this case, it's basically the slope, so it will be this arrow here, the blue arrow. So, and this is the notation, the partial derivative of L with respect to theta at the point theta equal to theta hat. This means at this point, if we start from this point, for example. And then what do? Well, we just move up. We move in the direction of the gradient. How much? As much as some positive scalar eta that we use here. So the new value for my estimate theta hat will be the previous value plus eta times the partial derivative of the likelihood function, the log likelihood with respect to theta, the gradient at that point. So I will move basically whatever the size of this arrow is times the parameter eta. I will move that much up and then I will reach another point, a new point like this ball here. And then what do? Well, I just repeat steps 2 and 3 until I finally converge. So basically from here I calculate again the gradient and then move again in the direction of the gradient and so on until practically the changes in the estimates of theta hat becomes smaller than some specified threshold. Okay, now for discrete CPDs, the optimal theta hat represents a probability distribution and hence must satisfy two constraints. The first one is that all entries of theta hat must belong to 0 and 1. And the second is that the entries of each CPD must add up to 1. Okay, now this of course puts some constraints in how we can use, for example, the gradient descent. How can we deal with it? We cannot just arbitrarily move into any direction. The direction should be such that these conditions are preserved. And the possible solutions are as follows. The first one is to use modified approaches such as conjugate gradient ascent method. The second is to reparameterize the problem by introducing a new parameter lambda of x condition on parents of x and then write the whole probability of the CPD in this way. Now, then I will just maximize the likelihood with respect to this parameter lambda. Now you see, if I do this, it's guaranteed that always, I'm just only optimizing with respect to lambda, but this is always positive and it's always adding up to 1 if I add up all the entries. Okay. And the third method is, well, instead of gradient ascent, we can just use constrained optimization methods such as Lagrange multipliers. The one that we're going to use in the upcoming example is a similar method to number 1 here, okay, which we will explain. To simplify the calculation of the gradient, we will need a couple of results, starting with this lemma. Consider a Bayesian network over the variables x1 to xn, and let O be a tuple of observations. For example, it can be the value of x1 and x5 or anything else. Now, the first result is that the partial derivative of the probability of those observations with respect to this CPD term, the probability of xi condition on its parents, is simply the joint probability of those observations together with xi and its parents divided by the term that we calculated the derivative with respect to. Okay. Now, using this, we can get this theorem that if we have a partially observed data set, D equal to O1 to On, now it's no longer a single instance, but it's a number of them, then the likelihood can be written in this form. So taking the derivative, this term you see that it is appearing, and the other terms it's just appearing as a conditional term, okay, over all the instances that we have, 1 to n. Great. And finally, we have the chain rule of derivatives, the partial derivative of the likelihood with respect to some parameter theta. It can be written in this form. It's the summation over xi and parents of xi, where the CPD corresponding to that, the conditional term, appears in the numerator and the denominator. They kind of cancel out, you can think of it. And then we have partial derivative with respect to this parameter theta. Just note that this is a bold theta including all the parameters. This is just one of them. Okay, just note that the gradient that I'm looking for looks like something like this, where it's a partial derivative with respect to some parameter theta, whereas these ones that I just presented are with respect to the probability of xi condition on these ones. So this is a probability, this is a parameter. Okay. Now if I want to transform this term into these ones, I need to use this chain rule of derivatives. Okay, so you see how I'm transferring them. Great, with these results in hand, let's get back to our original problem. We want to calculate the CPD in a case where the parents have missing values. So how can we solve this? Let's use gradient ascent, and actually here we're going to solve a more general case with 4 variables so that you see in a more complicated example here. I just added the node fever, and we limit the data set to only 2 instances here, O1 and O2. In both cases, mask and fever are known, but social distancing and COVID are unknown. Great. What do we want to do? We limit ourselves to just this part, the family of parameters, fever, condition, and COVID. Okay, the other parts can be done similarly. So we want to calculate the gradient of P of F condition on C0 given the observations. So namely these 2 terms. The gradient of the likelihood condition on theta of F0 condition on C0 and with respect to theta of F1 condition on C0. And what do we know? We assume that the current value of theta hat, it could be the initial value, it could be somewhere in the middle of the gradient ascent algorithm, we have these values for it. Okay, now we want to move to like our next ball, if you recall from the beginning slides, by using this gradient that we want to calculate here. So we want to update the parameter theta f1 condition on C0 and theta f0 condition on C0. Great. Now, just note that we don't need to calculate both of these terms because they add up to 1. So meaning that if we increase one of them by, say, 0.1, I have to decrease the other one by 0.1. Okay. Now, back to the chain rule. Just recall that the lemma and theorem that we presented, they were not in this form. They were with respect to P, the actual probability. So I have to transfer these two terms into those terms by using the chain rule of derivatives. Okay. So I will just make this term and the f1 term to appear here. And these ones are simple to calculate. Because of the equalities that I have, the first one will simply be 1. P of f0 condition on C0 is equal to the parameter. And the second one is 1 minus theta f0 condition on C0. So it's minus 1. Great. So I will have this equation that I can use. And I know this is 1 minus 1. And I only need to calculate this other terms that I have written here. Okay. So how to calculate these ones? The likelihood with respect to P of f1 condition on C0. Okay. So for the first one, just note that this parameter, the current value is 0.3 and the other one is 0.7. We'll take note of that. And we just know from the theorem that this term, the likelihood with respect to the probability of f1 condition on C0 can be written in this way. So summation over the observed values, if you recall from the theorem. So I need to calculate these two terms. Now for the first one, P of f1 and C0 condition on O1, just note that O1 has f0 in it. So having f1 condition on the fact that O1 is actually f0, this is equal to 0. I cannot have a different value of f given that the other different value is observed. What about the second term? Well, let's just use the definition of conditional probability. So I will have the numerator, the f1, c0, and O2 divided by the denominator. For the numerator, I will include the unobserved variable d here and marginalize it out so that I can decompose this term into according to the Bayesian network decomposition. And this is done according to the subgraph that we had here, probability of mass times probability of social distancing times probability of C condition on M and D times the probability of F condition on C. Okay, so if we do that, then we can calculate each of these terms. So the first one from the table that we have here, actually, the values that we have here, I see, like, for example, theta of M1 is 0.7. This is the first instance. For the second instance, I have 0.3. That's what I'm using here, and so on for the other values. So I will get 0.3 for M1, this one, and F1 condition on C0. This will also be 0.3. These ones will change according to the value of D. So I will have 0.5, 0.83, and for D itself, it's either 0.3 or 0.7. I will finally get this value, and similarly, I can do the calculation for P of O2 itself. This time, of course, I have to marginalize D and C, both of them, because I don't have F1 and C0 here. It's only O2. Now, using all this, back to my formula here. I just need to plug them in. So I will have 0 for the first one. And for this second one, I will have 0.07 divided by 0.13. And the whole thing times 1 divided by 0.3. So we'll get 1.68 as the gradient, as actually this term. It's not the gradient yet. I need another term, which is this one. How to calculate this? Well, it's similar to the previous case, just this time f0 is inconsistent with the second observation. So for this case, I will have 0. And for the first observation, this term, I will just do what I did in the previous case, marginalizing over d for the denominator. And for the denominator, I will marginalize over d and c. If you do the math, you will get these values. And at the end, I will get this partial derivative. So I have both of these partial derivatives with respect to p of f1 condition on c0 and f0 condition on c0. And using the chain rule of derivatives that I initially had, I will plug them in and I will get the final value for my gradient, this term here, minus 0.3. Consequently, the other one, theta of f1 condition on c0, this will be 0.3. Remember, we discussed that these two parameters add up to 1. Increasing one of them means decreasing the other one. So the updated values of my parameter, now I can calculate them for eta equal to 1, for example. Initially, theta of f0 and c0, this was 0.7. Now I got the gradient value of minus 0.3. For eta equal to 1, I will get the updated value of 0.4. And of course, the other one will be just 1 minus 0.4 because they add up to 1, so I will get 0.6. So you see that in this case, I even didn't need to calculate the gradient of the other. I could just update it using this rule. Great. Some final notes and some drawbacks as well. Just note that MAR or MCAR in some special cases is still assumed. Otherwise, we could not do any of this. We had to first model the observation mechanism. Okay, so the green light for using gradient ascent and also expectation maximization is MAR, is to have or to assume MAR. Now, gradient ascent is guaranteed to achieve a local maximum, not a global one. Okay, this is a drawback. It is an approximation. That's exactly why it's an approximation. Repeating the algorithm, though, can, for multiple random starting points, this can help to get a better estimation of this global maximum. Also, perturbing the convergence point, the locally optimal theta, and then rerunning the algorithm can help. In this case, we may get stuck at some point at some locally optimal theta, but then after perturbing it, we may fall into another area, and then optimizing, rerunning the algorithm may result in a better estimation. Thanks for your